Our planet stands at a turning point. Decades of reliance on fossil-based materials have driven progress, but also placed immense strain on our environment. Reducing consumption is vital, yet humanity will always need materials, and the question is, how should we make them, and from what raw materials? For the past 8 years, the FinnCERES Flagship program has explored answers hidden in nature's own design, unlocking the potential of lignocellulosic building blocks to create advanced bio-based materials. This is the story of a scientific journey towards a circular bioeconomy where innovation and sustainability meet.
Nature itself is a perfect example on circular economy. Non-human ecosystems are truly following this main principle that everything is reused, everything is repurposed, everything has a function, and no waste is generated. When this is translated to materials engineering and biomaterials engineering, it really makes a huge contribution to materials bioeconomy.
So if we think about the regenerative materials that we have around in countries like Finland, Sweden, Canada, it makes all the sense of the world that we try to use plants, biomass, and residues to create the materials of the future and to accomplish the mission of defossilization. And that is to use biocarbons to transform the economy from a hydrocarbon-based to a carbohydrate economy.
While well-managed forests are a prerequisite for any large-scale use of biomass, the next step is equally crucial: using this precious raw material in a sustainable manner.
So this entails that we use all the fractions efficiently, not only the cellulose. So biomass includes lignin, hemicelluloses, and extractives in addition to cellulose fraction. And this is exactly what we are doing in FinnCERES. We are utilizing all these fractions in an efficient way to produce high-value materials.
The new value-added materials actually often come from the biostreams and residues that yesterday were the source of energy, which is good, but now they can be actually the source of material production with much more higher value added.
The need for bio-based materials is here. We, FinnCERES researchers, have developed them. Now, we are working to provide evidence that they are not only environmentally better, but that they can compete in price, performance, and circularity with fossil counterparts.
Unlocking the full potential of biomass demands bold and innovative thinking. A critical area of focus is understanding how wood interacts with water. Water is the lifeblood of all plants and organisms on our planet. However, its mechanical role in trees, beyond just hydration and nutrient transport, has only recently been fully appreciated.
It is this way of looking at the water in plant cell wall that we consider it as a fourth structural element complementing cellulose, hemicelluloses, and lignin, which really provides the material's performance.
If you think about trees swaying in the wind, the elasticity and flexibility of trees is actually very different from wood, which has been felled. When you fell a tree or any plant, if you remove it from its native growth environment, it dehydrates. A plant fiber that has been dehydrated, removed of water largely, is a very different material from a living tissue.
The dehydrated fiber and its water interactions have been the headache of the pulp and paper industry for centuries.
Traditional limitation of paper is that once you put it in water, it loses its mechanical integrity.
The FinnCERES researchers at Aalto University and VTT are approaching this phenomenon from the opposite angle.
We are looking at how to utilize this instead of trying to prevent the water uptake.
We take the full advantage out of these water responsiveness, water interactions.
At the nanoscale, these water interactions become even more pronounced. This is the realm of nanocellulose.
The properties which are very intriguing from applications perspective is the high surface area and film formation ability, and also the peculiar behavior when it's in contact with water. These properties are very useful when we want to broaden the application fields, which can be towards high-tech applications, for example, for cellulosic and lignocellulosic materials in general.
One such application has been developed for the fight against microplastics pollution. This invisible enemy is threatening life in all its forms, and we are only starting to understand its effects. At FinnCERES, a research group led by Professor Tekla Tamminen-Peltonen developed a wood-based nanocellulose membrane that is able to entrap even the smallest nano-sized plastic particles, which are particularly difficult to capture otherwise. These membranes could help scientists all over the world to make accurate measurements on the quantities of nanoparticles in different water systems. In a step towards commercializing nanocellulose membranes, the FinnCERES project called AC Film is developing industrially viable bio-based water filtration membranes to meet the growing demand for new water purification systems required in the European Union.
The new Drinking Water EU directive that requires either the replacement of old pipelines or some type of device filtering the water just before the consumer uses it, and it is very expensive and challenging to replace whole underground systems in big cities.
Pressure-driven membrane filtration technologies are considered one of the most energy-efficient pathways for water purification. However, conventional membrane structures are fabricated using relatively expensive and synthetic materials.
Most of the available solutions nowadays to either big industries or consumers are made of fossil-based resources that can lead to the issues of microplastics.
The researchers have addressed these challenges by developing a nanocellulose membrane derived from wood, making it biodegradable and renewable.
Upon chemical modifications, we can introduce various functional groups which enable us to capture contaminants from the water.
We have identified promising findings from the economic feasibility analysis of the membranes. They are economically competitive and also perform as expected for ultrafiltration. Now we are looking to how do we scale up and how do we develop it further towards commercialization.
One of the major culprits in microplastics pollution is polyester clothing. Sadly, it is also the fastest growing textile fiber on the market. At the same time, cotton cultivation is facing an increasing number of environmental challenges.
Polyester is the dominant raw material currently in textile and fashion industry. It's very cost efficient, it's quite easy to use, but it's also causing several problems like microplastic pollution. And that's why we need to find replacements.
Wood-based cellulose as a raw material can offer a solution to this challenge. Currently, Finland hosts 6 new technologies to produce wood-based textile fibers. The Spinnova, Cura, Infina, IonCell, Noratex, and BioCellSol fibers are all contributing with their unique approach to a microplastic-free fashion industry.
In Finland, we have had interesting projects starting from fundamental science related to textile fibers. For example, how biomass can be used in new ways to create materials. And there are also science around to develop new finishings, waterproofing, for example, which is very important for the industry. Now we are starting to see how these ideas can be commercialized.
The recent advancements in producing textile fibers using ionic liquids now allow the presence of hemicellulose in the textile fiber, something that previously was a problem.
In the current man-made cellulosic fiber processes, the dominating raw material is dissolving grade pulp, where the hemicellulose is already removed from the pulping process.
Now, this costly step could possibly be skipped. In the FinnCERES spin-off project called SUPER, the role of hemicellulose in regenerated fibers has been studied in depth. Hemicellulose could even enhance textile fibers by bringing new beneficial properties.
Our hypothesis is that hemicellulose affects on the morphology of the fibers, and in that way we believe that we can have more porous fibers. When we have more porous textile fibers, we believe that the dye uptake is increased, which means that the kind of more sustainable dyeing methods can be employed for the fibers, and of course it can also create new application areas for textile fibers in these kind of applications where the moisture responsiveness is important, for example in sport clothing.
In addition to new fiber innovations, it is also crucial to look at the entire life cycle of all textiles. Every year, millions of tons of textile waste end up in landfills or incinerators, while less than 2% is actually recycled into new clothing. The FinnCERES project, led by researchers at Aalto University, is developing the scientific foundations to change that.
Most of these textiles that we are wearing are composed of different fibers.
Cotton and polyester are often mixed together, making separation difficult. Even small impurities can disrupt the recycling processes. To recycle textiles, we first need to understand what is inside the material.
If you have a garment, you can check the label, for instance, and it tells you what is in there, but only to some extent. It's never very accurate.
The researchers at Aalto analyze textile waste at a molecular level, revealing its exact composition. But this is only part of the challenge.
These materials, they are coming in different colors, and we need to remove this color in order to produce a white feedstock for textile recycling. When it's a white feedstock, it can be mixed with other white virgin fibers. But if it has color, it will hinder actually recycling and reduce the marketability.
To enable recycling, dyes must be removed without damaging the fibers. The solution can be found in existing chemistries, which are used in the pulp and paper industry.
Same kind of chemistries work also for cotton or the other cellulosic-based textile waste, because that is the same cellulose.
Once cleaned, the different fiber materials must be separated. But traditional methods often destroy one of them.
And we are aiming to preserve both the cotton and the polyester without dissolving or without degrading them.
Using water and air, fibers can be separated based on their surface properties with a method called flotation, allowing the reuse of both fiber types. Synthetic fibers require another step to close the loop.
We break them down chemically by using a hydrolysis method, and then that cuts down the polymers in the fibers into small molecules, which we can then polymerize back into polymers and then fibers eventually. They will have the same properties as the virgin materials have.
In a FinnCERES project called Cellulose, led by Professor Mikko Mäkelä, a multidisciplinary team of researchers are transforming the way we measure and predict the properties of recycled cellulosic textile fibers.
We've developed a new patented technology to estimate the degree of polymerization in cellulosic textile fibers. And it's important because specifically in chemical recycling of cellulosic fibers, you need to monitor and control degree of polymerization to enable spinning new man-made cellulosic textile fibers.
This patented method combines hyperspectral imaging with machine learning. Traditionally, measuring this key property requires a lengthy laboratory procedure.
Well, traditionally you evaluate the degree of polymerization as intrinsic viscosity, which is the standardized laboratory procedure. And I think it takes roughly 1 to 2 hours to complete in the lab.
The new approach reduces the time dramatically.
With our method, we can do it in less than 30 seconds.
These textile recycling projects lay the groundwork for more reliable and scalable textile recycling, turning used fabrics into future textiles. Alongside the challenges related to recycling textiles, the dyeing process is also a major environmental burden caused by the fashion industry. Currently, 99% of all dyes are made from fossil-based raw materials.
Most of the dye with the synthetic dyes is not adsorbed on the fiber, so it's lost to the effluents, and the effluents are then released to the rivers and lakes, and that is leading to the environment problems.
Finding sustainable, non-polluting alternatives is a high priority.
So we are developing bio-based dyes from existing side streams and also from fast-growing crops to provide one option to replace the synthetic dyes. We have been working with tree barks, such as with willow, and then with the Isatis tinctoria, that is dyer's woad, and it's producing indigo, the common dye used for dyeing jeans.
Bio-based dyes are not only non-toxic, but they can also have additional benefits.
So the beauty of these bio-based dyes is that you can get also the color, but you can also functionalize the fibers.
Plant-based molecules typically have inherent properties that bring both pigmentation, and they usually have UV active and antimicrobial properties.
In the PEF project, a fully bio-based screen printing dye was created using agricultural and food industry side streams.
The dyes we have been using have been onion skin and berry skin extracts. And in addition of these, we have used also coffee and green and black tea extracts. They are widely available and are produced in large scale, but they are not used for material applications.
What's more, the team has created a unique, fully bio-based binder for the screen printing ink.
So in the textile printing industry, commonly they use the binder system, which comprises of harmful chemicals. And then here at Aalto, we have developed a fully bio-based textile printing system with cellulosic fabrics. And then we have got an excellent results in terms of color fastness. Even we wash the printed fabrics like multiple times, we have got really good durability in it.
Nature is also capable of producing color without pigments. These are structural colors, created by the nanostructure of the surface material. In the Shimmering Wood project, a sustainable iridescent colorant was created.
Currently, the highly shiny and iridescent color effects are usually done with methods that are not very sustainable, using, for example, metal-based or plastic-based materials or toxic pigments. And we want to solve this problem by offering an alternative and making bio-based sustainable structural color.
So basically it's a thin layer of nanocellulose that can be applied on a variety of surfaces like metals or plastics or preferably wood. And in essence this coating is providing a strong iridescent color that doesn't require any pigments or dyes to give that color. And the color comes from the way the nanocellulose particles are organized within this coating in a special kind of helicoidal structure.
This research project has resulted in a startup called Shimber.
Many companies have approached us already during the research stage of the project. We noticed that there is not actually yet any other bio-based structural colorants in the application area that we are targeting. And also we have wanted to show that combining design and fashion and material science, you can make unique things and solve real-world problems beyond speculative concepts.
In another structural color discovery, Professor Monica Österberg's team at Aalto University was able to make brown lignin iridescent and transparent, completely by accident.
The goal was to make a more hydrophobic lignin so that I could make, for example, hydrophobic surface coatings.
In one of Alexander's experiments, things didn't go as planned, and the lignin dispersion turned out to be transparent.
And I thought that, okay, this is not at all what I had expected, but I have to do something with this. This is so special in some way.
Having discovered a transparent form of lignin, Alexander began searching for useful applications.
And I had read about anti-fog coatings before and how particles can be a very effective way of achieving super hydrophilic properties for anti-fog applications. And it turned out that these lignin particles worked like that as well.
When the coating is applied, for example, on the lens of diving goggles, it creates a hydrophilic layer that inhibits the formation of water droplets, or fog, on the lenses. But there are also substantial industrial needs for anti-fogging coatings.
For example, in agriculture, in these greenhouses, it's important that the sunlight comes through effectively. So fog is actually reducing crop yields also in these greenhouses.
The invisible lignin has already inspired the commercialization of an anti-fog lignin product for the consumer market by the company Boreal Bioproducts. But this was not the end of surprising discoveries.
I was preparing a sample for electron microscopy. And in the beginning, it was very simple. I just kind of added a droplet of the lignin particle dispersions. When it had dried, came back and saw that there were these kind of waves of different colors going kind of around the center of where the droplet had been.
We realized that when we have a thicker layer of the coating, some faint colors started appearing. And we were curious that this was not the color of the lignin, which should be brown. This was some more vibrant and colorful rainbow colors.
And Sahar, she was doing layer by layer deposition. And so I thought that maybe she would be able to figure a way to control the thickness.
What we achieved was, based on the thickness of our coating, we could get different colors, shade, such as blue, yellow, and purple. And just like nature, when we were looking at our coating from different angles, we were seeing different shades of color, exactly like butterfly wings.
But these colors look much brighter than paint, at least in some cases. So there are now some car models, for example, that have photonic coatings instead of just pigments.
For instance, it can be used for smart sensors that they want to be responsive to the environmental changes. It can be used for color-changing coating that they normally use for banknotes for security reasons.
Single-use plastic packaging remains one of the largest sources of pollution globally. The world produces around 350 million tons of plastic waste each year, and much of it still ends up in the oceans. To combat this monstrous problem, mathematicians, physicists, engineers, and designers teamed up to create a creative packaging solution using origami folding.
And the goal is to provide industrial level products.
And we have been focusing on Miurauri pattern because of the scalability of that pattern, so it's still relatively simple to do. And you can make very strong structure from a paper with just this pattern. Finding of the pattern in the modern time was from Koryo Miura, an astrophysician. It's a very used pattern in aerospace or airplane industry, since it has a lot of structural properties.
In the FOLD project, scientists at Aalto University and VTT, together with 8 industrial partners, have taken Miura origami folding to an industrial scale, enabling an affordable and continuous web production to cater to the packaging industry. In a FinnCERES and Aalto University spin-off, a sustainable wood-based replacement for plastic foams was created by the scientists behind the startup WOMI. This unique technology mimics the directional strength of wood, resulting in an exceptionally strong and light foam. The WOMI foam is highly protective and soft, yet non-toxic, fully bio-based, and recyclable in paper and cardboard streams.
We designed it to be a drop-in replacement for styrofoam. Basically, it's thermomoldable, so if you have a heat press, you can take a sheet of this foam wood material, put it into heat press and compress it, and it will stay in shape.
The key innovation behind the technology relies on a deep understanding of material physics, applied to a novel production process for the creation of a multifunctional product with adjustable mechanical properties thanks to the extrusion process.
During the extrusion process, the bubbles elongate. And when you have elongated bubbles in your foam, the fibers orient with these elongated bubbles. And so at the end, you get fibers between bubbles that are all pointing in the same direction. This gives the strength. Compression strength is 40 times stronger along the fibers than across the fibers. And this enables us to do very lightweight structures.
WOMI's patented technology is scalable and easily adjustable for diverse customer needs, making it an ideal solution for high-volume market adoption and positive environmental impact. In another wood-based foam application, Monica Österberg's group was able to produce a fully biodegradable dry foam made from nanocellulose. Normally, nanocellulose foams require expensive freeze-drying or oven drying, but the FinnCERES team has now been able to address this challenge.
We were able to produce the dry foam at room temperature without cross-linker with the simple method. So what's the science behind this? We use the lignin nanoparticle as a Pickering emulsifier that stabilizes low boiling point solvents. Meanwhile, we use the cellulose fibril as reinforcement and then polyphenol alcohol as a matrix to enhance the structure.
And what's more, the process can be scaled up to an industrial level.
The way we are doing, it can be basically done more or less in the same scale as paper machine or paper coaters. They could be used almost directly to make this kind of structure.
Forests have been and will be central to Finland's identity, vital for our climate, biodiversity, and economy. Yet the way we use them will change. As EU climate obligations require Finland to strengthen its forest carbon sink, the pressure to reduce annual fellings is growing, and with it, the imperative to create more value from less raw material. The Finnish Forest Bioeconomy Science Panel brings together leading researchers to provide science-based insights for sustainable forest use. Its mission: to turn research into knowledge that guides policy, innovation, and the future of our forests.
In a recent report by the Science Panel, we showed that added value products could increase the revenue from bioeconomy up to 80% compared to the level in 2019.
One scenario calculation what we did is that if we used 25% of that pulp which is now exported elsewhere, if we kept that in Finland and further refined it for more advanced products, we could achieve 3 billion euros of additional value in Finland.
Added value materials are becoming even more important due to the climate change and limits in fellings of trees. In terms of national resilience, this needs to be solved now. It cannot wait. Innovations and startups need a strong foundation in basic science and applied research, and it's our job as a flagship to support this.
Developing new advanced materials from lignocellulose, such as harnessing nanocellulose for entirely new high-value applications, will require a solid base in fundamental research.
To get nanocellulose into new application or advanced application, we'll need to understand fundamentals, both on interaction, so we can see how nanocellulose works, how they interact with other components. But it's also good to have fundamental research on how we produce the nanocellulose to get a good production method, and also how we can modify nanocellulose.
Inspired by the role of hemicellulose in the plant cell wall, Tekla Tammelen-Peltonen's team at VTT explores how its natural functions can be replicated in advanced materials engineering, such as the strengthening of nanocellulose.
Hemicellulose is a structural element in plant cell wall, and it is strongly interacting with cellulose. And together with cellulose, they provide the structural strength for the cell wall and for the plants. And in addition, they also are very hygroscopic, and they also hydrate the cell wall very efficiently.
However, heavily processed hemicellulose derived from pulping does not have the same properties as that of natural hemicellulose.
We have been using sources which are not that processed. We have been using the annual plant sources where, for example, the gelling ability of the hemicellulose is still retained. We have been working quite much with mixed linkage glucans. We believe that they behave better than these hemicellulose fractions which are much processed.
The mixed linkage glucans are readily available from a huge side stream. In Germany alone, 2.1 million tons of brewers' spent grain is produced, resulting in 21,000 tons of mixed linkage glucans annually.
We have developed fully biological hydrogels from nanocellulose materials and mixed linkage glucans. And these are possible due to mixed linkage glucans' inherent property of irreversibly cross-linking and binding to cellulose materials.
We have seen that the mixed linkage glucans interact very strongly with water, and they essentially form hydrogels at cellulose interfaces. And this property, combined with the inherent interactions with cellulose, is promising for novel applications where the material's hygroscopicity is important.
And these type of hydrogels, now they are fully biodegradable because all the components there are sourced from plant cell wall. And we have implemented living cells in this type of material. And we have been able to show that this hydrogel strength, even in submerged, harsh aqueous conditions, is strong enough that these hydrogels can accommodate living microorganisms which are producing desired components.
In a biotech application called the Futuro Leaf Project, nanocellulose was used to create a three-dimensional matrix for living cells. Here, microalgae is embedded into the nanocellulose and engineered to produce high-value chemicals.
The matrix is able to shield actually the cells from the environment. It has this potential to increase the fitness and also the general well-being of the cells. For example, it's able to shelter the cells from drying or varying amounts of, let's say, temperature or uneven light distribution.
Already today, the Futuro Leaf concept is applicable for the production of higher value products, like especially pharmaceuticals, but also specialty chemicals. And this counts especially because of the highly controllable and reproducible cultivation conditions the Futuro Leaf concept allows for.
Cellulose-based materials can play an interesting part in the medical field. Nanocellulose is not only an excellent matrix for microalgae, but it also provides a superior three-dimensional culture media for human cells.
All polysaccharide cross-linked matrices, they are not inert matrices. They are life-sustaining matrices for living materials.
Growing cells flat on a two-dimensional surface on a petri dish does not produce adequate physiology to the cells.
The 3D culture is more relevant because it actually mimics the environment in vivo. So you have the cells growing in 3 different axes instead of only one axis in a monolayer.
In a 3D matrix, for example, cancer cells and stem cells can be grown as 3-dimensional spheroids, offering well-formed cell physiology, for example, for drug testing.
These type of 3D cell culture, or we call the spheroids, they are a way of testing instead of using the animals.
However, the most widely used 3D culture medium, Matrigel, is derived from animal sources and comes with certain limitations.
If you are extracting the matrix from an animal, you have some batch-to-batch variability, and you have also different concerns about disease being transmitted from the material. Nanocellulose is more reproducible, so you don't have this much variability between one batch to another, and is also biocompatible and safe to use.
The high hygroscopicity of nanocellulose lends itself well also for drug detection. In a recent paper, nanocellulose was used in THC detection, the main psychoactive molecule in marijuana.
And there is a need for quick and easy detection systems for THC. We developed nanocellulose-based sensor material where we are utilizing the antibody conjugation to detect tetrahydrocannabinol from human saliva. And this sensor is very simple and fast, and it is based on color reaction between the sensor and the analyte.
In another drug sensing application, FinnCERES researchers took on a major challenge, drug poisonings, which cause thousands of deaths worldwide. A key factor in this challenge is time. Fast and accurate detection of drug molecules can mean the difference between life and death. Current diagnostics are relatively slow for molecules that are toxic in very low quantities, and it might take too long for the patient.
Usually a blood sample is drawn and it's sent to liquid chromatography. So at the best case scenario, you might have results in 2 hours, which might already be too late.
In the CellSens project, a multidisciplinary team is working on a novel solution to create fast, highly sensitive and selective small molecule sensors. The key component in the technology is combining carbon nanoparticles with bio-based nanocellulose.
Then we use sonication to make them properly mixed, and it will be a very stable dispersion for many years usually.
The carbon nanomaterials are the active elements in sensing. So typically we use electrochemistry, which is based on that we change the voltage and then we measure the current. So the carbon nanotubes provide the functionality, and then the nanocellulose is actually dispersing these very, very small entities very effectively, so we get a huge area. If we get a huge area, we get also large currents, and then we can detect very small amounts of molecules.
Not only do the two materials together offer high selectivity, but also high sensitivity, which solves a difficult problem in the field.
Medical diagnostics, I think the biggest problem is when you want to be able to detect drugs that are present in very low concentrations. Not only does our material need to be very sensitive to the drug that we want to detect, but it should be selective to only the drug and not everything else that is usually present in a human sample.
The key factor for higher sensitivity comes from the high hygroscopicity of nanocellulose.
And now when we put nanocellulose there, it attracts water there, and then we get more and more analyte to come with that influx of solvent.
The combination of these materials shows very promising detection results compared to current commercial solutions, achieving detection in the nanomolar range.
A commercial standard multi-wall carbon nanotube modified electrode, it's unable to detect, for example, 1 micromolar of dopamine or less than that. But simply with our nanocellulose and carbon nanotube mixture, we can push the detection limit down to few hundred nanomolars. So it is definitely going in the right direction.
In a surprising application, cellulose is made into optical fibers suitable for medical sensing.
They probably can't replace the classic optical fibers, which have a very small attenuation and you can transmit the signal for tens of kilometers. But there are lots of small-scale applications, for example, in biotechnical applications to mediate or sensing information from the tissues to outside world. So there one doesn't need to have tens of kilometers signal transmittance, but perhaps this length.
Although there are fossil-based solutions on the market, cellulose can offer superior properties.
This fiber can take humidity or water in the fiber. So the conventional glass optical fiber or polymer optical fiber, they cannot take water in. And this cellulose fiber also dries very fast, so we can utilize application where is this fast wetting and drying is needed.
And this is important because such fibers then can be used for measurements involving bodily fluid, for example, blood or sweat.
These unique features can provide a gateway to new applications where hydrophilic properties and biocompatibility are needed.
We have demonstrated spectroscopic measurements, we have demonstrated pH sensing, respiratory sensing, heart rate sensing.
This opens the door to a particularly valuable application, health monitoring inside MRI scanners, where most metal-based sensors and electrodes cannot safely be used. One of the most incredible discoveries has been the rate of data that can be transmitted within cellulose optical fibers.
We have shown that you can transmit optical signal with enough bandwidth to run 6 Ultra HD television channels in parallel. This demonstration shows that the potential of cellulose optical fibers is enormous.
These fibers can be considered a drop-in product to current wet spinning facilities for textile fibers.
Just making some small modifications, we are able to spin these optical fibers. So the infrastructure exists already in the industry and it can be tuned actually to make our optical fibers in the large scale.
With the advent of novel, sustainable, wood-based, high-value innovations, the pulping industry needs to renew in order to bring these new products on the market.
Sustainability actually began in forest-based industries over 300 years ago, and we have been practicing it ever since as a regenerative model for economy. We can still further grow and we can still further scale up, and that's an opportunity for Europe. But we are competing against the junk economy that is fossil, toxic, and addictive, and too cheap. And that's the real challenge for European economy.
One major issue for the future bioeconomy is to use all lignocellulosic fractions for high-value end use. Here, the use of lignin is in the spotlight. Lignin is a significant byproduct of the pulp and paper industry. Although it plays a crucial role in supplying renewable energy to the pulp mill, the amount of lignin produced exceeds the pulp mill's energy requirements. This opens up a huge potential for lignin-derived products.
Annually, 50 million tons of lignin is produced as a side stream from pulp industry alone. The majority of this lignin is burned for energy, but I think this is a waste of a great material that could be used much more efficiently.
An emerging area for lignin valorization is to use it to replace formaldehyde and phenolic compounds in adhesives and coatings. Professor Monica Österberg's group has developed a groundbreaking lignin innovation.
We take the technical lignin as we get it from the pulp industry, and we dissolve it in an organic solvent. We pour this dissolved lignin into water, and due to these molecular interactions between the lignin and the different solvents, they spontaneously form spherical particles. And this enables us to use it in traditional applications like adhesives, protective coatings, or composites.
In trees, lignin acts as glue in the cell wall. This property can be utilized to create bio-based strong adhesives. Replacing fossil-based compounds in construction materials like plywood or fiberwood can make some of these large volume materials recyclable. This lignin research has led to a startup called Lignosphere.
So we are building on at least a decade of direct basic research contributing to what we are doing at the moment. So we wouldn't be able to, get anywhere without the FinnCERES ecosystem support.
With industrial partners testing the Lignosphere's product, the application areas are expanding beyond wood.
We have been achieving great successes, for instance, in the areas of coatings on both metal and concrete, as well as some areas of adhesives.
Lignin is also a pivotal ingredient in an ongoing project at Aalto University, where Professor Michael Hummel's team has been able to make fully bio-based carbon fibers. Using bio-based precursors for carbon fibers has a long history.
Bio-based materials were the original precursor for carbon fibers at the very beginning of the development. But back in the days, and we're talking about 1960s, the fibers that were available at that time were not really good as precursors for carbon fibers. And then with the discovery of PAN, all these bio-based materials were more or less forgotten. They were insignificant.
But with the advent of ionic liquids and the ion cell process, the use of bio-based raw materials have gained new traction.
Ion cell process stands out for two reasons. One is that we can produce very uniform and strong precursor fibers, but also that we can dissolve and process more than cellulose, also other bio-based materials. And lignin is, of course, one of those that is very attractive. It's on the structure already a very good precursor, but also very carbon-rich.
In the future, these carbon fibers could be used, for example, in the automotive industry.
We are now talking about composite materials not for reinforcing parts, not for the chassis of the car, but for interior parts where producers are still keen on reducing weight in order to reduce the energy consumption of the vehicle when it's driven.
The lignin-containing ion cell fibers are carbonized in a unique, continuous process.
So our ambition is really to understand the transition step by step from a biopolymer, whether it's cellulose or lignin, to a fully carbon matrix. And we think by understanding this better, we can tailor the conditions in such a way that we are able to achieve these properties.
Another high-value application area for lignin is in batteries, replacing the fossil-based hard carbon. As we move forward with the green transition, the demand for energy storage is soaring. However, battery production depends on critical raw materials in quantities that exceed our present supply capabilities.
Batteries use a lot of critical raw materials. They use a lot of materials that have some supply chain issues here within Europe. And they also use materials that are mined, and there's some ethical and ecological concerns related to that.
Finding alternatives to the critical raw materials used in batteries is pivotal for our future.
So in the storage project, we really try to put together a whole working battery that is fully critical raw material free and could thus be produced anywhere. So we kind of depart from the dependency on certain critical minerals by replacing all the components pretty much with organic origin.
So in a battery we have an anode and a cathode and a separator with electrolyte in between. Typical lithium-ion battery would use graphite as the anode material and then typically a transition metal oxide as the cathode material and of course lithium in the electrolyte.
In this unique project, all of these components are replaced with non-critical raw materials.
In the anode material, in the negative electrode of the battery, we want to use a bio-based alternative material. So we want to produce hard carbon from bio-based feedstocks, which can be used as the anode.
The researchers have found that carbonized lignin works best.
And then instead of using lithium as the kind of current carrying ion in the battery, in the electrolyte, we are using sodium.
The sodium is mixed in a cellulose hydrogel.
So here we also make a stance and use purely cellulose-based materials that could also then, in theory, biodegrade, for instance, at the end of the life. The trick is to use some kind of high molecular weight cellulose so that it creates a nice film. And of course, we can explore this both in solid state and in a hydrogel state, and often in hydrogel state, the conduction is a bit better.
The cathode material typically contains cobalt, a toxic and critical raw material, which Jukka Niskanen's team at Aalto University is replacing with an organic, polymer-based alternative.
So we are working with these kind of redox active radicals, which we are attaching to a polymeric backbone, which can be used as the cathode material in the battery.
The active radicals are synthesized from vanillin, a lignin-derived aromatic compound. Putting all of these components together is a groundbreaking endeavor.
So it's not just about making a great separator or making great polymer-supported organic radicals, but it's about trying to make it actually work all together.
In a completely different high-value lignin application, scientists at Aalto University and VTT have created a bio-based black ink.
Black pigments are everywhere. So in the clothes we use, in the inks we used to write with, because of the contrast. In most plastics we use nowadays, it's always like a black component. And the market for this is actually huge. It's about 20 billion euro market, but most of it is heavily dominated by carbon black, which is a fossil-based source for black pigment.
And there are alternatives to make it from the biomass, but then really high energy processes are utilized, like thermal carbonization, for instance. Quite high temperatures are involved.
If we carbonize lignin in the normal process, we use pyrolysis, maybe gasification, but it needs temperatures more than 800. Sometimes it goes up to 1000 degrees.
The breakthrough came from developing a process that carbonizes lignin at much lower temperatures.
We convert this lignin into carbon using a chemical carbonization technique. We will mainly use an acid in an inert environment. This process happens at a lower temperature, maybe less than 200 degrees.
The carbonized lignin is combined with a nanocellulose binder to create the ink formulation.
We are approaching it initially with a ball milling process, which is again also very scalable and a very simple process.
Where our pigment will be mixed together with the fibrous material and grind it simultaneously, and the idea is the pigments would also act as the abrasive material to facilitate the fibrillation of the material, and also it would be a one-step process.
The pigment and ink could have broad application areas.
We see two main streams. One is that we use the black pigment itself, and that's one thing, and then the ink formulation, which is maybe like a continuation of is a next step. And for the pigment itself, we can pretty much embed that in any other matrix. For instance, if you want to make a plastic look black, we can use our ink formulations there.
Woody biomass also contains a small fraction of extractives, typically 2 to 5% in wood. Bark is much richer, with 10 to 30% extractives that provide the tree with natural waterproofing and protection. In birch bark, betulin is especially abundant. Its tiny crystalline structures are what give the bark its bright white color. Like lignin and hemicellulose, these compounds can be transformed into high-value materials instead of being burned or discarded.
There are many components in the bark which are interesting, but two of them are a lot more inspiring for us, especially one is suberin hydrolysate and the second one is bituline. These both compounds have very unique properties. So the idea for us was to utilize the waste bark and extract those compounds and transform them into functional nanomaterials. So these nanoparticles were very distinctive in their shapes, morphology. What we observed that bituline especially had a very good hydrophobic properties, and it gave us the water contact angle values approximately 160 and above. So this placed them into super hydrophobic materials. So this can be used as a replacement for PFAS.
PFAS are especially harmful because they persist in the environment and accumulate in living organisms. Replacing them with a bio-based and biodegradable alternative could have a major impact. Apart from using lignocellulose more efficiently and turning it into high-value products, alternative raw materials should also be considered. In collaboration with the Unite Flagship program, cattails grown on re-wetted peatlands were successfully converted into various biomaterials.
So we have made nanocellulose and lignin nanoparticles out of the cattail biomass. We are mainly using the stem for this, and our approach is that we don't want to form any waste but use as much as possible from the plant and still be able to make high value added materials.
These bio-based nanomaterials can be used for emulsion stabilization, so we have done some emulsion experiments with these materials separately and also combining the lignin and cellulose-based nanomaterial.
Emulsion stabilizers are used in products like cosmetics, where they are typically made from synthetic surfactants. This cattail-derived solution would enable a bio-based alternative. The team at VTT worked on several demonstrations.
What we did was to obtain lignin-containing CNF, or cellulose nanofibrils. We got inspired from the regular extraction of cellulose nanofibrils from kraft birch pulp, and we were able also to tailor the amount of lignin that they had.
In another demonstration made at VTT, all the parts of the plants were utilized to make a biocomposite material.
We produced a container for cosmetics. This was done grinding the full plant, having leaves, stems, all the sections of the plant there. And after that, we compounded with PLA. Then we end up having an extrusion that was pelletized. And with these pellets, we used injection molding to have these cups. This was performed in the pilot lines in Tampere. And then another approach that we have was foam forming, that we have also pilot lines in Jyväskylä. We used also the grinded whole plant and also blended with thermoplastic polymer and have these foam sheets that afterwards we thermoform, and we were able to manufacture cases.
But why use cattails? Cattails are an excellent perennial plant that can be used for restoring peatlands. Peat soils store centuries of carbon, but when drained for agriculture, they release vast amounts of CO2. In Finland alone, peat croplands emit around 10 million tons of CO2 every year. Preventing these emissions is a daunting problem.
There are management techniques where you can reduce the emissions, and reducing emission means that you should elevate the water table, And then you should have a crop species who grow well on those wet peat soils, and cattail is one of those. It's a kind of plant species which grows on all continents, and there is lots of traditional use for that species.
These actions could have an important impact on climate change mitigation.
And by converting them to cattail production, we can reduce the emission. In best case, it might be a reduction of 35 tons of CO2 equivalent per hectare per year.
One of the challenges, however, stems from harvesting in wet conditions, which will require specialized machinery.
It depends what you produce from cattail. If you're happy to have a dry material, you can harvest in wintertime, but if you want to have fresh, green material, then you have to invent machinery which harvests that in summertime.
We can make these nanoparticles from dry or fresh biomass. This enables harvesting of the cattail also in wintertime.
Apart from using alternative raw material sources, the pulping method itself plays a substantial role in resource efficiency. In the FinnCERES spin-off, called the Emission-Free Pulping Program, the current status quo is challenged by creating innovative processes that fundamentally differ from traditional kraft pulping. The goal is not to modify existing methods, but to produce entirely new concepts that will benefit the global pulping industry.
With the current processes, what the forest industries are using and the pulping industries are using is kraft pulping, where we are using only 50% of the wood to products and the rest of the 50% is burnt, which means we are not utilizing 50% of the biomasses.
The emission-free pulping program aims to increase the pulp yield from 50% to 70%. But a major challenge lies in retaining the quality of the fibers.
How to strike a balance between the product yield, quality of the product yield, and how to develop a process which is far more efficient than the current processes, but not too expensive, but not generating waste, not generating emissions.
If we increase the fiber yield, then the fiber will be different what we have today or what we are used to having today. So we also need to find some qualities and some products where these new fibers can be used and how they are going to be used. For instance, molded products is one, textiles could be one, different type of textiles, technical textiles, non-wovens, and so on, so on. So there can be good products available for the new fibers coming out from EFP.
As we move away from fossil fuels, a new challenge is emerging: the carbon gap. We still need a source for carbon to produce fuels, chemicals, and materials, but fossil carbon must be replaced.
Biogenic carbon dioxide emissions is a vast and underutilized feedstock for chemicals.
Project Co-Foam is developing cellulose-based foams for water-assisted CO2 capture, turning pulp mill emissions into a new source of renewable carbon.
And this would not be capturing carbon dioxide from the atmosphere directly, but actually from the exhaust pipes directly at the site of its generation in the industry.
Most existing capture technologies rely on liquid amine scrubbing.
And then later the CO2 is released from there by simple heating. The heating takes a lot of energy in this traditional way.
The release of the CO2 is necessary if it is to be used as feedstock for new chemicals or materials.
Actually, the high energy intensity of existing technologies is very often considered as a main bottleneck or challenge for upscaling the carbon capture technologies.
Project Co-Foam explores a solid bio-based alternative, one that avoids energy-intensive heating in the release of captured carbon.
The nice thing about this whole idea is that we could release the CO2 by merely adding a little bit of acid there, so changing the pH. And that would release the CO2 instead of heating it. We would use a solid substrate, and those would be actually foams, high surface area foams made from ordinary pulp fibers.
The idea is to increase the surface area of the capturing surfaces by incorporating nanochitin or nanocellulose, which we have functionalized with amine groups. And solid solvent capturing, when compared with existing technologies, holds much promise and future potential in carbon dioxide capturing and utilization.
The future of the forest products and pulping industry will depend upon new innovations that take full advantage of the natural properties of woody biomass. Going forward, modeling AI and machine learning will revolutionize materials engineering and significantly accelerate the path from laboratory to commercial applications.
My personal hope that it will be something which is supporting, providing tool which is enhancing us to do science in future faster. So I think what we do in the lab should verify our modeling results and enable that we pivot early enough and we become faster to come into good proof of concepts.
At the same time, using less of this precious material to make higher value products is the only way to move forward.
Our industry has over 900 years of history in Europe, yet FinnCERES has managed to bring a completely fresh perspective to the material that we use, new, better solutions for the big challenges that we all face.
I think the research that's been conducted within the FinnCERES has made a remarkable impact on the global scientific community. It's opportunities to focus in depth on some themes and really publish and present what has been achieved has really brought a lot of value to the scientific community.
Behind every breakthrough in FinnCERES stands a network of over 50 industrial and academic partners from across the world. This collaboration between researchers, industry, SMEs, and society has been the engine of the program, generating discoveries with global impact.
What we said at the very beginning in FinnCERES was global challenge requires global networks. FinnCERES has different lines of work, not only domestically with VTT and the Finnish industry, but also abroad. And today we have the Border Alliance that is starting to yield many fruits.
It's really important to collaborate international in the cellulose research community. We can learn from others, we can use others' infrastructure for experiment, instrument, we can get help on analysis, and it's also good to get new ideas.
When it comes to the industrial collaboration, I think that we have been successful because we have had many spin-off projects from FinnCERES together with industry. It was even a surprise for us how this fundamental approach of utilizing water interactions in materials engineering and translating that into technical fiber systems, that has been gaining so much interest also from industry perspective.
So the fundamental science or basic science, it generates the basis of new innovations because it provides new knowledge, and it also provides like curiosity-driven insights to the topic. And those are extremely important. They are actually essential for the new innovations and new knowledge.
I believe it's very important that the academic setting takes responsibility and has the opportunity to conduct the fundamental research, as that is not possible for the industries. But it's also very important that there are mechanisms that translates the fundamental research into something that is digestible for the industrial partners. And looking at FinnCERES a little bit from the outside, I believe that you have sort of managed to bridge the gap between academia and the industrial landscape.
Now we know where to go, and I think the opportunity now is to transition from the lab scale to a larger scale, to de-risk the technologies and create business opportunities. And I think this is going to be possible. There are many challenges, but the science is already there. And I think FinnCERES has contributed tremendously in these efforts.
In FinnCERES, totally more than 300 invention disclosures have been made, and also more than 100 patent applications have been filed. One can say that somehow connected to FinnCERES, around 10 new startups have been founded.
There is no better time to rethink how we approach science and technology in the Finnish ecosystem, to become more resource independent, to advance local technologies, and I think FinnCERES can be a great instrument for that purpose.
When we are talking about FinnCERES, I think we are talking very much renewing of scientific agenda, and I think that's a continuous process. So I hope that we continue having platforms where we enable curiosity-driven research, and at the same time we demand excellence, and we demand that we force us to carry out very intensive discussions with the industry to ensure that we do things which are relevant for the industry.
Today the society is again in transition, and if the next industrial era is circular bioeconomy, then we are already its foundation. We invest with the horizon of 20 years in a world that changes every 2. We plant trees for a future that only our grandchildren will see. And we bet on science for tomorrow that we don't know yet. It takes courage, but our industry has it.